Good afternoon, everyone. Thank you for the introduction, and thank you for this opportunity to present to you one of the aspects of the research that goes on in the QFOT Center. Now, my research focuses on materials devices, and device physics, and particularly in what we call two-dimensional materials. Now, in order for the rest of this talk to make sense to you, I first need to introduce what we mean by two-dimensional materials. Now, as we know, solids, the atoms are arranged in a 3D lattice, but materials exist where those bonds between different layers are very weak, van der Waals bonds, and you can very easily peel off different layers from the material. And if you've ever written with a pencil, that's exactly what you're doing. The graphite in the pencil is leaving graphite on the page. It's been mechanically exfoliated from the graphite. And graphene, which is the 2D version of graphite in your pencil, is one of the most famous 2D materials. But actually, there's a whole family that includes semiconductors, such as MOS2 or WSE2, insulators, for example, HBN, and various others. Now, my research particularly focuses on this material, WSE2. And a crystal of this material looks a little bit like this. You can see it's got a flaky type structure. And in the lab, what we do is we take a piece of sticky tape, stick it onto your crystal. You can then peel that tape off. You're left with some material on the surface of that sticky flake. You then stick that onto a host substrate. We use silicon wafers, which have a layer of silicon dioxide on top. And then you peel the tape off, which leaves you with some two-dimensional material on the surface of your substrate, which you can then look at under a microscope, find flakes of different size, different thickness, find the one you want, and continue the rest of the fabrication process. One particular advantage of these kind of materials is that you can stack them, as shown by this graphic here. You can think of it a little bit like stacking Lego blocks, where each block represents a different material. If you do that and combine different materials, you can change their electronic properties. Or, as in the work that I'm going to be presenting to you, we can sandwich layers of WSE2 between insulating layers of boron nitride, which improve the quality of our devices. Now, our lab focuses on the application of these materials, particularly in transistors. Now, why and how are 2D materials useful in transistor applications? Well, as we know, the electronics industry is really driven with the goal of making more efficient and smaller devices. So you want to pack a larger number of transistors on a single chip that consume less power. And at first, that scaling, or that reducing of transistor size, was basically through reducing the size of the transistor in this planar FET traditional structure, making them thinner, narrower, but you start to run into problems, particularly with silicon materials, where if it's too thin, your interface starts to affect the carrier transport. If it's too narrow, you start to get leakage currents. And so that drove this development of different transistor designs, basically where you have a gate that wraps around your conducting channel, or you then separate your conducting channel into different nanowires, or latest developments are these nanosheet transistors. I selected a couple of examples. They're a little bit old now, but they're from two giants in the electronics industry, just to show you how important this is. Now, if we look at a cross-section of a set of these gate-all-around FETs from IBM, we can see that in this case we have 5 nanometers thick and 40 nanometers wide. And so it's not a really big leap of the imagination just to imagine that we could replace these materials with our 2D materials to make these transistors even smaller. If we want to think a little bit more quantitatively, we can think in terms of Moore's law scaling. So basically that the number of transistors on an integrated chip will double roughly every 2 years. Initially, as I mentioned, this trend, we could follow this trend just by scaling the dimensions of transistors themselves. Then it was necessary to change the design of the transistors. But in order to continue following this trend, we're now at the point where we're reaching the limit of traditional designs, traditional materials. And so the aim, really at the forefront of research, is to integrate different kinds of materials, two-dimensional materials, or like changing or introducing different kind of transistor operations. So why are 2D materials so helpful in this regard compared to silicon? Well, it's illustrated quite helpfully with this graphic here. If you look at, this is the thickness of your material. Silicon, as it becomes thinner, the carrier mobility drops very rapidly. Whereas in two-dimensional materials, which is this group of materials up here, even in the monolayer limit, so just one atom thick, that's the ultimate, that's the thinnest material that you could possibly make is 1 atom thick. So in 2D materials here, you still retain a good enough carrier mobility, or I should say a much better carrier mobility compared to silicon, which allows you to continue to make these efficient transistors. The reason for that is that these 2D materials, their surfaces are free from dangling bonds, which are basically trap sites, which will reduce your mobility. And as well, you can integrate them with 2D dielectrics, such as boron nitride, which has a much lower surface roughness than silicon dioxide. So that's another way of reducing the disorder in these structures. So what do our 2D transistors look like? Well, I'll talk a little bit more about the fabrication process in a couple of slides later on. But basically, here simply put, we take a silicon wafer, which is highly doped, so that acts as a gate electrode for us to control the carrier density. So that's our back gate. That has a layer of silicon dioxide on top, so it's an insulator. And then we put a layer of boron nitride on top of that thin layer, which just gives us a nice surface for our 2D material to sit on. And once we've transferred our 2D material, we then evaporate our metal contacts. And in this structure, remember I said that we could stack 2D materials, and that's what we've done here, except we've covered half of our material stack with a layer of HBN. Half of it is still left open. And I've shown you this really just to illustrate why we're particularly interested in tungsten diselenide, WSC2, this material. And that's because you can get N or P-type transistor behavior, just depending upon differences in your fabrication process. That could be depending upon the type of metal you integrate. It could be the method that you use to make your metal contacts, for example, using traditional metal evaporation techniques or transferring the contacts. The material thickness will also affect the characteristics. But the process that we use is this oxygen plasma treatment. So that when you expose the surface of your tungsten diselenide to an oxygen plasma, it converts the top layer here to a tungsten oxide, which is a charge transfer dopant layer, and that will induce holes in your tungsten diselenide below and create strong P-type behavior. So when we measure, it's here on this left-hand side, the part that hasn't been exposed to our oxygen plasma, then we see this blue trace. So it's the intrinsic properties of our tungsten diselenide. So we have a larger current for a positive gate voltage, so it's showing stronger N-type characteristics, whereas on this side that's been exposed to an oxygen plasma, we see a very strong P-type behavior. So current turns on for a negative gate voltage. And we can use that to really just to do a couple of things. Firstly, we just demonstrate that we have a nice PN diode using this technique. So we do that just by showing if you change the bias, you get a larger current in one